Continuing from our abbreviated lecture on Wednesday, there will be, I assume, no tornado drills today. We're going to talk some more about rocks. So this is the last slide, I think, that I showed you. Is that right? Look approximately the same. So things that we use, physical properties that we use to identify different minerals. And so you see there we have things like how hard it is. What does it mean for something to be hard?
How hard you just break it.
That's actually not what it is. That's why I asked the question. How hard is going to be how hard it is to damage it, not to break it. To break it would be how brittle it is. And so hard and brittle are slightly different things. So to measure the hardness, what you do is you see if you can scratch it. And so you could take something like a piece of copper, like a penny, and a piece of aluminum like this, and see if the copper scratches the aluminum or if the aluminum scratches the copper. The one that gets the scratch is the softer one. The one that does the scratching is the harder. So you probably know the answer. What is the hardest material, or what we usually say, what is the hardest material known to man? Diamond. Now, I think I've read somewhere that they found a novel material that might be harder than diamond, but diamond is at least the standard answer for the hardest material. For measuring hardness, we use the Mohs hardness scale. That's MOHS. And diamond is a 10. And sapphire is a 9. And it goes on down. We'll see the scale in a little bit. And to actually test this, you don't just try to scratch one thing with another. You have a little diamond-tipped indenter, and you put a certain amount of pressure, and you measure how big the indentation was that it made, and that's what tells you the hardness. So there is a scientific way of measuring it. But the hardness is based on different materials. So you have something like talc, T-A-L-C. I don't know how you pronounce that word. Talc. It's very soft, very easy to damage. Lead. Has anybody played around with lead? Come on. I should be able to find a piece of lead real simple. Actually, there's a bunch sitting on my desk in my office. But we can play around with lead later. Lead is super soft. You can easily scratch lead with your fingernail. So it's a very soft material. So that's what the hardness is. The crystal form, that's the structure. If you look here, we have, I know, not very good quality picture, but we have different structures for the crystals. It's kind of hard to see them there. Here, pyrite, you can see a very clear structure. You see that you have a sharp edge there, a sharp edge there, sharp edge there. Now it's got something there that's not a sharp edge, and sharp edge there. Very angular. And this has very much rectangular angles. That's its structure. That's what we're talking about when we say it's structure. Now, we do more careful measurements than just, oh, that looks, to get it. But that's what we mean by looking at its crystal form. Cleavage and fracture. Cleavage is when you take a crystal, you have the atoms are in a reproducible pattern. And so you have some planes where the force between atoms is weaker. And then it's easy to just take a razor blade and you tap it with a mallet and it splits on that plane where they're not so strongly held together. That's how you cut a diamond. The diamond cutter very carefully figures out where the cleavage planes are and has this pattern he's trying to make, he or she, puts his little knife blade there and gives it a tap and splits it. As you might imagine, if you do it wrong, you've just wasted a whole lot of value in the diamonds. So those guys have to be super careful. But that's cleaving. And so you could take one of my samples, this crystal in here. Where's that calcite? You could take this and you can see, okay, it has a flat plane here. So if I take a razor blade and I align it so it's parallel with that plane, and then I carefully tap it, it should split. And I had to do that with my samples in graduate school. I had to do a whole lot of cleaving of my crystals to get a nice smooth face that I would hit with my laser beam. Color is pretty clear. Density, we've talked about density and the importance of measuring density already. And another one that it doesn't have here that I mentioned is streak. And no, streak has nothing to do with sporting events and clothing. Streak is, you take the streak plate, this thing here, and you take the rock and you go and you look to see if it leaves a colored streak, and if so, what color it is. Neither of those left a colored streak. This one I'll bet you will. Yeah, see, that one left something. And sometimes the color that the streak is surprising. It's not what you expect. So that's actually another measurement. So that's why the streak plate is in here, so that you can do that. And of course, this here, the top is a simple magnifier. So you can take this sample here that has a bunch of crystals that you can see with the naked eye that are small. You can bring it up here and see the crystals better. So every good field geologist is going to have a few things with them. They're going to have a magnifier, probably a better one than this. They're going to have a magnifier. They're going to have a little bottle of acid. What's the little acid for? I've mentioned it before, but not today. It's a chemical test, not a physical test, hence not in this list. What dissolves in acid? What kind of rock dissolves in acid? Limestone. And so if you have a rock that you think might be limestone, you drip a little acid on it, and if it dissolves, if it starts to bubble, then you're like, aha, it has.
Is that the only rock that dissolves it?
Limestone's not the only one. Dolomite, which is actually calcium carbonate, and I think it's magnesium carbonate. Right, so it still has the carbonates and will still do the same thing. If it was straight magnesium carbonate, it would still do the same thing. But that's a chemical test, and this is a list of physical tests, so that's why it's not here. But those are things that you have. Another thing that every field geologist is going to have is something for scale. You know, you see pictures of rocks or fossils or things like that, and they always put something in there so you can tell what the size is. It might be a coin, because everybody has coins. You can pull out a penny and say, that thing is this big because I can tell from the size of the penny. Or they might have a little ruler that's not just a regular ruler, but has like a block that's black and a block that's white, and then has it marked off so that the blocks are easier to measure off to determine size. You know, so they have something that's a scale, so you can take a picture with the scale in the picture, and then you have reference for size, other people have reference for size. One last thing I remember is a little hammer. Got to have a little hammer. One side has a sharp edge for digging, and one side has a blunt edge for tapping, so that you can break things and dig things. Okay, I already talked about crystallization, so let's skip right past that. The crystalline shape, the form, has to do with the way the atoms are packed, and I think I have some pictures. Yes, pictures say a lot. So here are two different things. I don't have any diamond in this box. Not surprising. Graphite and diamond are both 100% carbon, but they don't look at all alike. So, well, actually, this here is mica. It's not graphite. Actually, no, it says it is graphite. So here's graphite. Graphite is a sheet. It will break off easily in sheets. I don't want to split this because there's only there. I split it. That's how easily it splits. You don't need a sharp device. The carbon atoms in mica are forming flat bonds, so that they're bonding with things in this direction, but not at all in this direction. So the only thing that you have to hold it together in this direction is going to be very, very weak intermolecular forces, Hence, that graphite is easily split, and one sheet can slide over the next sheet very easily. That's used by people. They'll take this and grind it up and use it as something to lubricate locks because the stuff will slide over real easily. So here is a picture showing the graphite structure. If you look at the structure, you see that you have the flat sheets of linked hexagonal rings. So there's a hexagon. And so those rings are making a strong sheet, but as I said, only very weak forces to connect one sheet to another. Whereas if you look at diamond, the diamond structure is very complex. You have each carbon atom is forming 4 bonds to other carbon atoms. But then those bonds, if you try to make a ring, there, you can make a ring. That's a hexagonal ring, kind of, but it's not a flat hexagonal ring. And you could have made that ring also going in different, I should have done that with different colors now, shouldn't I? Here's another ring sharing 2 of the, or 3 of the same atoms. And so you have multiple rings that are made in a 3-dimensional structure, making it a very strong structure. So diamond and graphite, exactly the same element. They're both elemental. It's only one type of element. But different crystal structure makes a world of difference. Nobody pays, 1 month's salary for a graphite ring. But they do pay a month's salary for a diamond ring, which is silly because it's just a thing. Wouldn't you rather spend that money on a honeymoon than on a thing you put on your finger? Huh? 3 months? Goodness, I don't know. I am very opposed to the what I consider very dishonest, monopolistic diamond cartel. And so, yeah, while my wife does wear a diamond ring, it's one she got from her grandmother because I was not going to support the diamond industry. So if you want to see a diamond ring, Amy has one, but I did not buy it. As a side note, jewelry, if you're going to collect it, make sure you know values and stuff. We inherited some from Amy's grandmother, and we didn't know what to do with it. I'm sure we lost thousands of dollars in value because we didn't know the value of any of our jewelry. So here are pictures. This is a diamond here, clearly. That is, I believe, coal, which is another form of carbon. So carbon can have different forms based on the crystal structure, and this is the one that costs you a lot of money. So you're not paying a lot of money for the carbon atoms because, after all, carbon is reasonably common. You're paying a lot because it's hard to get that structure. Now, just as an addendum, since I've talked about the evil diamond cartels, in the last decade or so, scientists have developed ways of making man-made diamonds. When I was in graduate school, one of my buddies was doing research on diamond-like films, trying to figure out how to make things like diamond. And they've gone past that so they can make them. What's the difference in a man-made diamond and a diamond made in the ground?
I don't know, really. You can't really, I heard that you can't really tell the difference of which one's which. Yeah.
You can somewhat. The man-made diamond can be made perfect, whereas the one in the ground is probably not going to be perfect. Now, you can introduce impurities in the man-made one to match whatever you want. So you can make a diamond of any color, clarity, whatever you want with a man-made one. So basically, the man-made ones are going to be your higher quality diamonds. But the diamond cartels are trying to convince people that those are the cheesy ones that you don't want. You want the real one that was made in the ground. No reason whatsoever you should want the real one that was made in the ground. One more thing to say about this. What's a blood diamond?
I don't know, but I've seen the movie.
I don't know, I've seen the movie. Well, if you've seen the movie, you should know.
It was a while ago. It was a long time.
Because I grew up I lived in Sierra Leone for 2 years and Liberia for 3 years. The blood diamond thing is something that's from, the land I grew up in. Blood diamonds are diamonds that are not going through the diamond cartel. They call them blood diamonds because they're, in theory at least, supporting somebody's war effort. And so the diamonds that have gone through the diamond cartel, they have little laser etched identification numbers on them. The blood diamonds don't, because they're not going through the cartel. You do probably want to stay clear of those if you want to have a clear conscience, because you're supporting a war effort. Much like if you buy gasoline for your car, you're supporting a war effort probably. But nobody talks about blood oil. Okay, so enough on these political type topics. Let's get back to other properties. I talked about the hardness. Here's the Mohs scale. You can see the word Moh. Don't be a Moh. And here are the basic values for hardness. So you see diamond is 10. It says corundum. That corundum does not look like a gemstone, does it? What did I say? Corundum and sapphire are the same thing. Sapphire is the name given to it when it's used as a gemstone. Corundum is the name used for the mineral. If you look at that picture, that does not look like a gemstone, does it? What does the sapphire look like? The sapphires I did research on, my master's degree was specifically studying sapphires, where it looked like glass. They were transparent. Because mine were man-made, it's not that hard to make man-made sapphires, and they were made very pure. Pure sapphire is just like glass. The kind that you buy as a gemstone has impurities in it to give it the colors. And so blue, I think, is the most common color. You can also have green, and there are some other less common colors that you can get for your sapphires. But those are impurities, once again, that are giving them the colors. And corundum is, like I said, the name for the mineral. I'm going to erase that because it makes it hard to read. So it's a hard material. It's a very transparent material in its pure form. So sapphire is kind of like the poor man's diamond in terms of it's almost as hard as diamond. It's almost just, good properties in most respects as diamond. And then you have topaz 8. Quartz is a 7. Quartz, basically sand. We'll learn more about that in a minute. Orthoclase, I don't know what orthoclase is there. Not. Anyway, this one here, apatite, not to be confused with I'm hungry. Fluorite, calcite. Calcite, you see, is a soft thing, but what's really, really soft? Talc. And notice the fingernail is here between 2 and 3. So I said that you can scratch lead with your fingernail. That means lead is lower than about 2.5. Of course, your fingernail probably won't scratch a copper penny, right? So that had to have been a harder thing, not a lot harder. And you can go on up and see common things. The masonry drill bit has to be really hard because you want to break through other hard rocks. Right, masonry is cutting through rock. So those are basic ideas for how hard something is. So if you're a geologist out in the field, you're going to use things like this to get a rough idea of the hardness rather than using the actual hardness tester that you would take it back to the lab and do. And yes, I did hardness testing on my sapphire. Got a little experience with that too. Here we can see some actual pictures of how the cleavage works. So you have this here is something that looks like my graphite did. It's something that's in flat planes. Its cleavage plane is only in that flat. And you saw I was able to, quote, cleave with my fingernails with that graphite. Then you have, here's an example with cleavage planes in two directions that are perpendicular to each other. So that's feldspar, so you could cleave it along either a vertical or a horizontal on that line, and it would split off nice and easily. If you put your knife edge in anything that's not aligned with either the yellow or the white, it would not easily split. And if you break it, it will usually break, so you have some planes of one and some planes of the other. And then feldspar here is an example where you have three cleavage planes that are all perpendicular. Then you get to halite. What's halite? You use it every day. That's good thinking. Not it, but that's good thinking. You eat it every day. Table salt. So table salt, it has three cleavage planes there, but they're at angles. So it cleaves a little differently. And so, yeah, I thought it had pictures over there. The only picture it has is that one. So that's, you can tell some clear differences in looking at a crystal based on the cleavage planes. And you see the fluorite here, it's an octahedral crystal that breaks on 4 cleavage planes, so it's more cool still. The diamond shapes they make are based on the cleavage planes of the diamond. So, you get the very complicated patterns. Let's see, where's the diamond we had? This here is a very complicated pattern of flat surfaces, and each of those flat surfaces, so for instance, there's a flat surface, and it's hard to tell where the flat surfaces are on this, but there's 2 sides. I think it goes like that. And then there's, I think, a different cap down here as well. I'm not into the cutting of diamonds, so I'm not sure. But each one of those is a different cleavage plane. And the person who's cutting it has to carefully cut on each one. Now, can you take something, let's say sapphire, doesn't have the same cleavage planes as diamond. Can you take a sapphire and make it look like a diamond? You can, but you don't do it by cleaving. You have to polish it. You have to, make a rough cut. So you use a diamond tip blade or something to go and grind through it. And then you can polish it, and it will look something like this, but they're not the natural cleavage planes. They're not going to be the exact angles. They're as close as you could get. And of course, it's not going to have the same optical properties, because another difference of diamond, something that makes diamond have its sparkle, is that light goes really slowly in diamond. The speed of light in diamond is speed of light for diamond and for sapphire C is the speed of light in vacuum. In diamond, the speed of light is about 2/5 the speed of light in vacuum. Whereas in sapphire, I think it's like 1.76. I'm probably wrong in the last digit there. But that's a fair amount faster in sapphire. And because it's faster in sapphire, it actually has different refraction, bending of light, and looks differently. And so the sapphire will never fool a person who knows their diamonds, because you have the different speed of light in it.
But by looking at it, like just naturally, would you be able to tell? Or is that something that unless you like knew the difference?
You would have to know the difference in how the light is going to sparkle. But there would be a difference. And of course, most of your fake diamonds aren't sapphire, because that's too expensive to make a fake. They use cubic zirconia. No, as a replacement for diamond in a fake diamond ring. They use cubic zirconium, which it's cubic. Its cleavage planes are cubic. That's why it's called cubic. So clearly you can't cleave it into the shape of a diamond, but what you can do is cut and polish it. Okay, colors. What's the difference in these three things? The color's the obvious one. You can also see that there is a different cut to it. All of these are cut differently, but what do they have in common? They're all the same thing. They're all sapphires, but this one here, I think it's iron. It might be, yeah, I think it's iron is the impurity to give it the blue look. Iron can give you a blue or a green or a rust color, brownish look. Depends on the ionization state. We talked about that. This here has a chromium impurity, and that's what gives it the red color. And this here, pure. So all of those are the same thing, but you have little impurities, little imperfections in the atoms that give you the different colors. And then the shapes are different because they were cleaved differently. Person chose different. You know, you still have the same faces. This face here should be the same as this face here, but the difference is they made it longer on one edge to give it a more oval top. So it's just the way the person cut the rest of it or cleaved it. Here are some other examples. I believe these are all sapphire over here on the right, other colors that you can get that are less common. And of course, I always call it sapphire. I should probably say corundum. So the color is because of impurities in there usually. Our first of the clicker questions in probably 2 days, well, 2 lectures. Physical properties of a mineral are predominantly related to which things?
Almost there. It like has to like go all the way in.
Yeah. There we go. All right, we had 0, 3, 5, 0. Now, I randomly chose you, Ashton, to be the first of 3 people to answer. Which one did you select, Ashton?
I put B and C.
Well, you put B. Let's go with B. Why did you put B? Okay, then why would you have chosen C?
Because those are really different properties, mineral properties. Those will form part of its imaging fracture and density.
Okay, these are the physical properties. So those are the physical properties. So she's saying they're predominantly related to what the measurable properties are. Okay, Rachel, did you agree with her?
Yeah.
Then I'm going to ask you A. Why did you not choose A?
Because C was a better answer. I was going to choose A if I didn't choose C, but I didn't know specifically why I looked.
Okay. I know it's a little harder to answer why did you not choose it than why did you choose. This here, the external conditions of temperature, pressure, amount of space available for growth, those dictate the form, which is right there. So that is, right, when we talk about physical properties of a mineral predominantly related to, we can interpret it different ways. Why does it have these physical properties? Because of external conditions of temperature, pressure, and the amount of space when it formed. Right, so that would also be a fair answer because it's, it dictates the physical properties. And then for our last one, Ivy, you are going to have to defend B, whether you answered it or not.
Well, I didn't answer that one,
Gabby is here to help.
more complex atoms are put together in stronger than their own case.
Okay. What you're saying is part of the answer. Right? The chemical composition and the internal arrangement are going to make different minerals. Right? If you have calcium carbonate, it's not going to make the same mineral as if you have just, let's say aluminum, it's aluminum oxide, it's Al2O3 for sapphire. It's just not going to make the same mineral. So the chemical composition it's got to be different minerals. But as we saw with the diamond, which is what you were specifically referring to, the diamond has all of those interlocking bonds that makes a very strong three-dimensional structure, whereas the exact same atoms formed in a different environment form the flat sheets that are very different. So both the chemical composition and the arrangement of the atoms, what made the arrangement of the atoms? The temperature, pressure, and amount of space. So the best answer, in my opinion, would be all of the above because the question is a little too broad. Each one is, depending on how you interpret the question, the right answer. Once again, for test questions, I try not to be so broad that you could say, well, they're all correct. Okay, classification of rock-forming minerals. So fundamental separation, silicates versus non-silicate. Or if you're into Bill and Ted's Excellent Adventure, non-silicate minerals and non-silicate minerals. That'd be silicate. So silicate minerals are 90% of the Earth's crust. What are silicate minerals? Well, clearly they're important. Silicate minerals are silicon and oxygen based. And then you have other things, aluminum, magnesium, iron, manganese, and titanium that it lists here. But they're silicon oxygen based, so silicate. What is the base unit for the silicate? This is the silicon, and these are oxygens. So there's your unit cell for a silicate. SiO, how many O's are there? 4. Now, if you make a silicate structure, you will change this a little bit so that quartz is actually SiO2 is quartz, which is our most common silicate rock. So silicates are based on silicon as the center with oxygens around it. Of these silicates, we subdivide it into ferromagnesian silicates. Ferro means iron. Notice my color coordination here. Ferro means iron. And magnesium very clearly has magnesium in it. So iron and magnesium containing, and then our other one here is non-ferromagnesian. Question, Lindsay, I don't know where I am. Leslie.
Are we going to see pictures to show the distinguishing how they look different?
We're going to have a table, and the table has pictures. A table with a diagram, like with our chemistry test. If this, then this. It's, spreading them out. So yes, we will. In the non-ferromagnesian ones, then you further break things down. And so you have low density and light color feldspars, which is a field rock because it's the kind of stuff they found in the rock, that contain a lot of aluminum, sodium, potassium, and calcium. And that's roughly half of the Earth's crust. Roughly half of the Earth's crust is feldspar. So you know what? If you pick up a rock and somebody says, what is this? If you have no clue, say feldspar. It's a 50-50. So here are some picture examples of non-silicate rocks, the 8% remaining. And so you have halite, that's our rock salt. I pronounce that spinel, but I don't know.
Wait, what are these?
These are non-silicate. These are common enough rocks. Remember, they're only 8% of the rocks that don't contain silicon oxide. They contain oxygen for sure, right? Spinel has the 4. Gypsum, this is a water and calcium sulfate. Hematite, that's an iron-containing ore. It's magnetic. I talked about the Earth's magnetic field flipping in class yesterday, or lab yesterday. And it's hematite in the basaltic floor of the ocean that has the magnetic information because iron is a magnetic material. And so they're looking at the magnetic orientation of the iron in the hematite. Calcium carbonate. Pyrite, iron sulfide. Pyrite is also known as fool's gold. It's the stuff I used to always see the flakes of in the creek when I was a kid and say, is this gold? My dad would always have to say, no. Is this gold? No. Is this gold? No. I was sure I was going to get rich. And one of my favorites, galena. That sample does not look nearly as pretty as many samples. Actually, if I remember right, the sample in this box is not super pretty either. I don't even see it right now. I know I picked it out last class period. Yeah, here it is. But the galena, to me, is one of your prettier minerals, especially if you get a nice sample. So the types of non-silicates are carbonates, things with calcium carbonate. Dolomite, remember I said that's magnesium carbonate and calcium carbonate. Oxides, oxides, they have oxygen attached. So hematite is iron with oxygen. Hema. Where else do you hear the prefix hema? Actually, it's hemo in the form I'm looking for. Your hemoglobin? Your red blood cells? Why are they red? It's because that hema that also means iron. So hematite is iron oxide. Your blood is red because of the iron. Magnetite, I don't know what it is offhand. Chromite, obviously it's going to be chromium. The ore minerals, pyrite, galena, sulfates, we've already gone through. Native elements. Clearly native elements don't have silicon dioxide in them or silicon silicates in them. So gold is a native. So here is what I was talking about for the classification. All minerals fall into either silicates or non-silicates. And then the silicates are ferromagnesian or non-ferromagnesian. And so we have 3 examples here of ferromagnesian, things that contain iron and or magnesium, and things that are non-ferromagnesian, things that don't. And here you can see, here's the difference between plagioclase and orthoclase. They're both feldspars. They're both the field rocks. And then over here, the non-silicates, we've already looked at those. So just pictures. And you have this picture in your textbook as well. That gold picture is, there we go. It's looking less than exciting. Our next clicker question. The silicates are the most common and abundant mineral group because silicon and oxygen are all but one of these are true, but only one's correct. Guys, true statements, but not the reason they're the most abundant. Stick up the weight on one. No, waiting for Sarah. Is it somehow disconnected?
Yeah, it says no window on channel.
How many have we answered so far? We've answered 2, right? Or is it only one? Only one? Well, we'll figure it out. I'm going to go on because he can't answer. So we had 1600 for our answers. 6 people went with the one that's the correct reason. The 2 most abundant elements in the Earth's crust, are silicon and oxygen because of their low densities compared to iron, the most abundant element on Earth, being a higher density. So that's the reason that it's the most common, because it's the one we have the most of the elements for. Not the hardest, right? The diamond is, after all, the hardest. Quartz in our hardness wasn't up there. Found in mineral quartz? Well, sure, it is found in the mineral quartz, right? Quartz is our classic silicate rock, but that's not the reason it's abundant. Quartz is abundant because the silicates are abundant. And yes, it is a tetrahedral structure for the silicate, but that's not why it's common. So how do minerals form? Minerals form either from being melted and solidifying or in an aqueous environment where they crystallize. The ones that are melted and solidify are usually going to be, well, they're always by definition going to be the igneous rocks, but those are usually going to be silicate-based rocks. The ones in water solution are likely to be something else, like calcite or dolomite or something like that. So those are the 2 environments in which the minerals form. In both cases, it's going to take time to grow crystals of reasonable size. So when you find a large-sized crystal, it means that it took a while in that environment for it to form. So if you have a large crystal in an igneous rock, in a rock that used to be melted, it had to cool very slowly. So our understanding is that granite, which has reasonably large, like millimeter or more sized crystals in it, probably cooled for millions of years in the process. So you have millions of years for these little crystals to grow. Now, I'm going to point out right here a contrary opinion. How many people have heard of Robert Gentry or his plychoric, I don't know, something like that, halos? No one? Well, what he has found, Robert Gentry was working in Oak Ridge National Laboratory, and he was studying samples of granite. And so he has a nice flat piece of granite. It's been carefully cut, and then he's looking at it with a microscope, and he finds these little halos. Now, those halos have a very easy definition for how they got there. You have radioactive elements, uranium, is a radioactive element that is naturally occurring in the Earth. When uranium decays, it gives off an alpha particle and goes to thorium. So it has an alpha particle coming off, but the alpha particle is carrying energy. And when that alpha particle hits another atom, it's likely to give up its energy. But when it does, it will send a shock wave through the material. So the alpha particle is not going to travel very far. Remember, you can block alpha particles with just a piece of paper. So it doesn't travel very far at all from the uranium, and then the energy of the alpha is absorbed, and it makes a circle, a shock wave, that leaves a scar, if you will, a halo, with a radius, and that radius is proportional to how much energy the alpha particle had. Well, the thorium is going to decay, and the thorium can either give off an alpha or beta. But the decay process, you start uranium, and you end up at lead. So going from uranium to lead, as a general rule, let's just say everything's alpha. It goes uranium, thorium, radium, radon, polonium, lead. Right? There's other steps along the way because you have some beta particles, but that's the basic process. And so most of these decays, it's got a half-life of like 1,000,000 years, 100,000 years. It's going to be a long time from one decay to the next. But, and I can't remember if it's the radium to radon or the radon to polonium, but one of those has a short half-life. Actually, I'm pretty sure it's the polonium that has the half-life, decaying to lead. And so what he found was little halos that had the halo for the polonium, if I have the elements right, the polonium to lead halo, but doesn't have the radon to polonium halo. And then you're like, wait a minute. The half-life of the radon, if I have these things right, is like 3 minutes, which means that, if you wait 10 minutes, you should have somewhere on the order of 1/3 times 1/3 times 1/3 remaining. That would be 1/27 remaining, or roughly 4% remaining, is that right? So if you have 4% remaining just after 10 minutes, it's really, really unlikely that you're going to have years between one decay to the next. And for this to form, that is for you to have the halo, it has to be solid rock at this point. It can't be liquid rock or you don't preserve the halo. And so he said, well, what's going on here must be that God created the rock with polonium in it so that you only have the polonium halo and not the radon halo. Because if it was natural, it would have started with uranium, and it can't move, so it would have had to have both the radon and the polonium halo. So he uses that as an argument that God created granite looking old, except that he didn't create it with the halos to make it look old. Now, some people consider that really strong evidence against creation, or against evolution, and other people don't. But it's interesting because it's talking about that crystallization and the time it takes. So Gentry says, unless granite can form in a matter of minutes, that this indicates that, the granite was formed with these halos already in it. Okay, we're going to have to stop at this one here. Things that cause crystallization to occur faster or slower. So when you have things crystallizing in a melted form, the things that crystallize with a high melting temperature will crystallize first. Things that crystallize at a low melting temperature will crystallize last because, of course, it takes a while to get there. And then you have other things here. Silicon content. If you have low silicon content, that equates to having a higher melting temperature, and so it melts or it freezes earlier. A high silicon content, it will freeze later. And, of course, melting is the reverse of freezing. So these things go together. If it doesn't have much silicate, it's going to have a higher melting temperature. It will crystallize first and melt last. If it has high silicon content, then it will be the last one. I don't know why I have M there. It will melt first and crystallize last. So the amount of silicate in the mineral indicates what its melting temperature is. Okay, have a happy Sabbath, a great weekend. Happy Easter, happy April Fools.